Hey guys, if you are in Cal, this is from 3.6, and if you are in pre-Cal and we're learning calculus at the end of the year, this is from 4.6, and this is called curve sketching. This lesson is not a new lesson. It has no new information. This is just us taking everything we learn and starting to put it together. Very important. So let me give you a list of steps of suggestions, and what's going to happen in this lesson is I'm going to give you a function, and you're going to use everything you've learned to get as much info about it as possible to then do as detailed as possible a sketch of that function. Okay? So again, you can follow these steps in a different order. This is the one that I suggest, but let's look into it. Okay? So first, even going back since algebra 2 is where the majority of these first steps come from, and then from 4 on, the second half is more calculus. Okay, so step 1, x and y intercept. Step 2 is finding the symmetry of the function. Step 3 is looking at the continuity, meaning checking if it has any vertical or horizontal asymptotes, and checking if the domain and range gets split at any point with holes or jumps. Now moving on to what we've learned in calculus, checking the end behavior. The way we check end behavior is seeing where the function goes on each of the ends, meaning on positive and negative infinity. So we'll use the limit at infinity that we just went over. And then step 5, we'll use the first derivative rule to find where it's increasing, decreasing, and where it has a max or min. And then we'll use the second derivative test to find points of inflection and concavity. Okay? So let's go ahead and look at this first question. I want to give you a second option. Anytime I see a question like this, I know that I can use it as is, or I can distribute that 2 and call it 2x squared minus 18 over x squared minus 4. So that's going to give me the ability to use it in 2 different ways depending on what I feel is easiest for myself, okay? So step 1, let's look for the x and y intercept. The way we solve for x-intercepts is by setting the y equal to 0. Okay? So the y is the f of x. It's setting the entire function equal to 0. And again, you can use either one of these two. I'll go ahead and use the first one. If I want 2 times x squared minus 9 over x squared minus 4 to equal 0, remember, in order for a fraction to equal 0, only the numerator has to equal 0. Okay? Because 0 over anything equals 0. If you don't remember that, you would just multiply this denominator over, which anything times 0 is 0. So what I'm really working with on my next step here is 2 times x squared minus 9 equals 0. I divide the 2 over. I move the 9 over. And then I square root the 9, and remember, every square root has a plus or minus 3. Okay, so my x-intercepts are going to be 3, 0, because remember I set the y equal to 0, and it's going to be negative 3, 0. Okay, let's go ahead and find the y-intercept. This one's a little easier. The way I find y-intercepts is by setting the x equal to 0. So if I say 2 times 0 squared minus 9 over 0 squared minus 4, okay, I end up here with 2 times negative 9 over negative 4, which just gives me negative 18 over negative 4, which can be reduced to 9 over 2. Okay, so my y-intercept is 0, 9 over 2. Okay, so there is step 1. That's 2 bits of information I've already found. Let's keep going. The next thing to do is to find symmetry. Okay? So in symmetry, this is going to be useful because I can find out if the function is going to be identical left and right, or top and bottom, or corner to corner, or if it's not going to have any symmetry at all. So being that I see that both are squared, I'm going to want to test for symmetry with respect to the y-axis. Because squared functions, like if I think of a parabola, are usually the same on the left and the right, okay? Now there's obviously some movement going on here, but let's check out symmetry with respect to the y-axis. So the way we check symmetry with respect to the y-axis is by plugging in a negative x, okay? If you don't recall this, there's a nice review section in the beginning of your textbook. Go to the very back of the textbook and look up symmetry, and you'll see it in that review chapter. Okay? So I'm just going to plug in a negative x into the function. So it would say 2 times negative x squared minus 9 over negative x squared minus 4. Okay? And symmetry says that if you plug in a negative x into the function and it comes out identical to what it was, then in the negative x values and the positive x values, you'll have identical y's. So it will be symmetric with respect to y. So the fact negative x squared gives me a positive x squared. And same down here, negative x squared gives me a positive x squared. And I do end up with the exact same function. So check mark, I am symmetric with respect to y. That means that whatever happens on the right side of this graph is going to be identical on the left side of this graph, okay? So let's move on to our next step, which is continuity. So the first thing I'm going to do for continuity is check vertical asymptotes. Vertical asymptotes are found by setting the denominator equal to 0. Okay, so I see that I have a vertical asymptote at positive and negative 2. Okay, and then that vertical asymptotes going up and down are going to affect my domain and my range. Excuse me, specifically my domain. So now I know that I have vertical asymptotes at positive and negative 2. That means when I read the graph left to right for my domain, I'm going to have to take a pause at positive and negative 2. So I could say my domain is negative infinity up to negative 2. Then I'll go from negative 2 to positive 2. So I only took a break here at negative 2. And then I'll go from positive 2 on to infinity. So you can see my break here at negative 2 and my break at positive 2. Whoops. Sorry about that. Next, I'm going to check my horizontal asymptotes. And just a quick recap, the way that I know these are vertical asymptotes and not holes is because that denominator, and let's look back at the original, x squared minus 4 cannot be canceled with an x squared minus 9. If you could cancel them out, then it would be a hole, but since they cannot be canceled out, that's how I can confirm that they are vertical asymptotes, okay? So now back to horizontal asymptotes, which we did in limits and we recapped last lesson, is if they have the same exponent, which we can see that they have the same exponent. Let's look right here. Right? X squared and x squared. We use our coefficients to determine where our asymptote is. So our horizontal asymptote is at y equals a over b, which in this case would be 2 over 1, which is just at 2. Okay? So that means my range is going to get split up. If I have a horizontal asymptote Now when I look at the graph up and down, I can go from negative infinity, but I have to pause at 2, and then I can go from 2 on. If you feel like you struggle with writing domain and range, maybe I would suggest finishing the whole process of drawing the graph and then writing out your domain and range. It might feel a little easier to see the visual. All right. So let's move on to end behavior. In order to check for end behavior, I'm going to do the limit as x approaches infinity, okay? Okay, and I'm going to do that for the function. My function is 2x squared minus 18 over x squared minus 4, okay? So again, remember with infinities, I can use a horizontal asymptote rule, and I can see already that my answer is going to be 2. If you don't feel confident moving that quickly, you plug in the infinity. Right? Infinity squared times a number minus a small number. I'm still going to get infinity over infinity, which is an indeterminate, which allows me to do L'Hopital's. Derivative here would give me 4x. Derivative of 18 is 0. Over, this is going to give me 2x. Okay, derivative of negative 4 is 0. And before I finish this, I'm going to reduce 4x over 2x and say the limit as x approaches infinity of the x's will cancel out, and then 4 divided by 2 is 2. And then the limit of any constant is just that constant, okay? So I know that as I shoot out towards infinity, I'm going to be approaching 2. Okay, there's my end behavior. Let's move on to the next step. Step 5 is the first derivative test. So my first derivative test says to complete, obviously, the first derivative. Let's use this same function that we had written here. Again, you could use the one without the 2 distributed, same thing. So f prime of x is going to be low d high minus high d low over low squared. Okay. Now I can clean this. I'm going to distribute the 4x, distribute the 2x, and distribute that negative. Okay. So 4x times x squared gives me a 4x cubed. 4x times negative 4 is a minus 16x. Remember here I'm distributing a 2x and a negative, so I end up with minus 4x cubed and then plus 36x. Just rewriting the denominator. And I'm going to clean one more time because the 4x cubed positive and negative are going to cancel out. And then I have a negative 16x and a positive 36x, which leaves me with 20x over x squared minus 4 squared. And I need to check this equal to 0 or undefined. Okay? So if I'm checking it equal to 0, I'm setting the numerator equal to 0. And if I'm checking equal to undefined, I am setting the denominator equal to 0. Okay? Here, if I divide the 20, I get x equals 0. Here, if I square root both sides, I'm left with x squared minus 4 equals 0. Move the 4 over, and then square root the 4. Okay? So now, at this point, I'm going to want to draw my number line, including these 3 spots. I'm going to come up here, just to not waste too much space. Now, on my number line, I have 0, I have -2, and I have +2. Now, the whole point of this lesson is to start piecing everything together. Now, this positive and -2 has come out before, okay? If we look at our previous work, we saw down here that positive and -2 were vertical asymptotes, okay? Just like an elbows graph, it would make sense that the increase, decrease, or concavity would look different on either side of an asymptote, okay? So, in my opinion, if you recognize that, it'd be important to put an asymptote there, because even if I have a change in an increase and decrease, it doesn't mean that this is a max or a min, because these are asymptotes. It's not part of the graph. Okay, so now I'm going to test my in-betweens. I'm going to say f prime of a number before, let's say -3. F prime of a number in here, let's say -1. F prime of a number in here, let's say +1. And then f prime of a number out here, let's say +3. So if this is our derivative, okay, since the denominator is squared at the end, no matter what I plug in, I will be dividing by a positive, because anything squared equals a positive. So I'll always be dividing by a positive. Now, if I say 20 times -3, I'll have a negative. 20 times -1, I'll have a negative. 20 times +1, I'll have a positive. And 20 times +3 is going to be a positive. Negative divided by positive is negative, so that would tell us we are decreasing. Negative divided by positive is a negative, so we are decreasing. And then these two positive divided by positives will give me positives, which means I am increasing. Okay? So far I know this is negative and negative. So decrease, decrease. And then positive, positive. So increase, increase. And I can see that this switch in decrease to increase is going to give me a min. Okay? Now, I can clearly see my intervals of increase and decrease here. I'm increasing from 0 to 2. Take that pause at 2. Okay, remember, there's always a reason why they make you pause. And then from 2 to infinity. And then I'm decreasing from -infinity to -2 and -2 to 0. All right, and then I know that I don't have any maxes, but I do have a min. And my min is going to be at 0, and I need to plug that 0 back into the original to find out the location. So let's flip over here. Okay. These were my two functions I was looking at. If I plug in a 0, let's look at this right one, into these two x's, these first two terms are going to disappear, and I have -18 over -4, which reduces to +9/2. Look familiar? My minimum is the same as my y-intercept. Okay? So if I plug this 0 back into the original, I get 9/2. And then we'll make a quick statement and say that there was no max. Just so when we look back, we can make sure we didn't forget max, okay? All right. All right, let's move on to our second derivative test and the last part before we sketch. All right, so if I'm finding my second derivative, let's look back at what the answer to my first derivative was. I'm going to do low d high, derivative of the top, minus high d low. Be careful, the derivative of that low is a chain rule. I have derivative of the outside, rewrite the inside, subtract 1 from the exponent, and then times derivative of the inside. All over this low squared. Okay? So now, remember when we talked about second derivative test, we said that almost every time we do a second derivative, instead of having to clean all this craziness, we should in each of the three terms, so here's one term, here's the second, and here's the third. In each of the three terms, we should be able to find something in common. And check it out. X squared minus 4, there's 2 of them. X squared minus 4, there's 1 of them. And x squared minus 4, 2 to the second, there's 4 of them. Okay? So that means I can take 1 out of each. I'm going to take 1 complete one out of here. I'm going to take 1 out of here, and there's going to be 1 left. And remember, 2 to the second, an exponent to an exponent, you multiply. There were 4, and now there's going to be 3. Okay? So this can become 20 times x squared minus 4 to the first. I'm allowed to just distribute that. So I'm going to have 20x squared minus 80. Now here, the only thing I have left is the negative 20x, the 2, and the 2x. So I'm going to end up with negative 2 times 2 is 4. 4 times 2 is 8. So negative 80. And then there's 2 x's, so x squared. Okay? All over that same denominator, which is now cubed. Okay? And I'm going to clean one last time. I have, when I combine these two, I have negative 60 x squared minus 80 over x squared minus 4 to the third. I need to set this equal to 0 or undefined. So if I set it equal to 0, I only have to set the numerator equal to 0. So now I divide the negative 60, and then square root of 0 is just 0. And now to set it, undefined, I set the denominator equal to 0, which you should start to notice is going to work out the same as when you did it up here. I'm going to cube root 0, which is just 0. Which again, we remember those as being our vertical asymptotes. Let's scoot up a little bit. So now I'm going to do my number line. Let's come up here. So I've got, actually I'm going to do it right here. Okay. So I have negative 2 0, and 2 as my possible points of inflection. But again, I remember that -2 and +2 were asymptotes. And now, this part I'm going to do up here. I need to plug values into my second derivative. So, to the left of -2, I'm going to put -3. In here, I'm going to put -1. In here, I'm going to put +1. And in here, I'm going to put +3. Okay? Now, this is my second derivative. Because the exponent here is cubed, I cannot assume that this is always going to be positive. So this is going to take a little more of a thought process, okay? Because a cubed keeps whatever sign took place in here. So let's take one thing at a time. If I say -3 squared, it's going to be +9. +9 times a negative is going to give me a big negative. A big negative minus more is going to stay negative. Okay? Divided by -3 squared is going to give me a +9 minus 4. It's going to give me a positive number, and a positive cubed will be positive. Okay? Negative divided by positive is negative, which is going to give me concave down. Let's do the -1. -1 squared is going to be a +1. So this is going to be -60 minus 80. It's going to be negative. Now here, -1 squared is going to be a +1. 1 minus 4 is a -3. -3 cubed will stay negative. Negative divided by negative is a positive, which will give me concave up. Okay? All right. Now putting in a +1. 1 squared is 1. 1 times -60 is -60 minus 80 is still negative. And now if I put a +1 in here, I'll get 1 minus 4, which is -3 again. A -3 cubed is still negative. So negative divided by negative is positive, which gives me concave up. All right, last one, 3. 3 squared is 9. 9 times a -60 is a big negative number. Minus some more is going to keep me negative. And then a +3 squared is going to be 9. 9 minus 4 is a positive number. Positive number cubed is going to stay positive. Remember, odd exponents keep the sign, okay? Negative divided by positive is negative, and now I am concave down. Okay? So let's just add that information down here. I have negative, which is concave down. Then I have concave up. Then concave up again. And then I have concave down. Okay? So I'm concave up from -2 to 0 and from 0 to 2. I'm concave down is from -infinity to -2, and then from 2 to infinity. Now, I know we're used to seeing our points of inflection in between our switch and concavity, which technically change in concavity happens here at -2 and 2, but because -2 and 2 are asymptotes, they are not part of the actual graph, so I cannot list some ordered pair. So technically, I have none. And if you want to write yourself a side note, it's because of the vertical asymptotes. Okay? All right, you are done with the work. It is time to just put this to a graph. Oops. Okay? So I've gone ahead and drawn this 10 by 10 graph. Okay? And all I'm going to do is that work that we just went over, it should all be in your notes. I'm just going to go step by step and start putting things on this graph. Okay? So the first thing that I know that happens, according to my list, is x and y intercepts, okay? So I know that I have x-intercepts at -3, so 1, 2, 3, comma 0, and at +3, comma 0. Okay, I know those 2 points are going to exist on my graph. I also know that at 9/2, which 9/2 is 4.5, I have a y-intercept. Now that also happens to be my min. So if it's a min of something, I'm going to write the word min underneath because I know it'll be the lowest point of something happening here. Okay? Now, I do know that it's going to be symmetric, so you can already see that what's happening on the right is happening identical on the left. The next thing that I have is my continuity. I know that I have 2 vertical asymptotes, one at +2 and one at -2. I also, sorry, bear with my drawings there, it's a little sideways. I also know that I have a horizontal asymptote at +2. So at +2, I'm going to draw my horizontal asymptote. Okay? So that's what my asymptote should look like. Okay? Moving on, I know that my end behavior is going to shoot out towards 2. So that's something I can keep in mind as I draw. Now, my first derivative test says that I'm going to start off decreasing. So look, I don't know if I can fit it all here at once. As you look at this graph, I also want you to look specifically at this part of your notes, okay? And at this part of your notes, okay? That's what I'm going to be looking at as I talk. So the first thing that I see happening before the asymptote at -2 is that it is decreasing and that it is concave down, okay? So on this side, I'm going to be decreasing and concave down, and I have to hit this point in my graph. So the fact that I have this dot here lets me know it's going to happen underneath and not above the horizontal asymptote. And I'm going to draw something that is decreasing and concave down. And we could always use the concept that I ride along asymptotes, okay, to help us out. Next in my drawing, after -2, I am decreasing and concave up until 0. So, and I have to hit this point. So decreasing and concave up until 0. And then after 0, I see an arrow that shows me I'm increasing and concave up, which also lets me see my min and my y-intercept, okay? And then lastly, after that asymptote at 2, I see an arrow going up for increasing. I see that I'm concave down, and I know that I need to hit this point. And I also know I'm symmetric, so it should look identical to the other side. So I'm using all the bits of information from my work to be able to draw a function as accurate as possible. And with that, you are done.